Good evening, everybody, and thank you for joining us for this Cafe Sci. My name is Dan Lavoie, and I'm honored to be your host this evening. Cafe Sci is presented by PPG. Cafe Sci is also supported by the good people like you. Thank you to everyone who donated to support this program. If you are unable to donate, but still would like to support Cafe Sci, the most helpful thing you can do is invite your friends and family to join the audience. Cafe Sci takes place the first Monday of each month, and you can register for the next month's Cafe Sci at CaymanScienceCenter.org. Before I introduce tonight's speakers, I'd like to remind everyone that we are now streaming on YouTube. We'll be taking Q&A questions from our YouTube audience as well as our live audience tonight. If you are live in our YouTube chat, please hold your questions until the Q&A period begins. Please include a first name when asking the question, and I'll collect them from the chat and get to as many as time allows. It's my pleasure to introduce tonight's speakers. Jared Rackley is a meteorologist and forecaster with NOAA's National Weather Service at Pittsburgh, where he has been serving the area since 2018. He holds both a Bachelor of Science and a Master of Science in Geography and Atmospheric Sciences from the University of Georgia. Jared's career with NWS began in 2016 at the NWS office in Lake Charles, LA. Before joining the NWS, his professional role was as a nuclear forensic meteorologist at Oak Ridge National Laboratory. In his free time, Jared enjoys spending time outdoors, doing photography and traveling. Tonight, I also have a special guest, Liana Lubo, is a meteorologist with the National Weather Service here in Pittsburgh, where she joined the office in 2024. She earned both a Bachelor of Science in Meteorology and a Master of Science in Applied Meteorology from Plymouth State University. Before joining NWS, Liana served nearly 6 years as a senior meteorologist at route analyst at Weather Routing Incorporated, supporting marine forecasting and operations. Her early experience includes research at Texas A&M University through a National Science Foundation-funded research experience for undergraduates. I'd like to welcome both of our guests tonight. Thank you.
Well, good evening, everyone that's here. Thanks for joining us, and thanks for having us. We're always happy to get out into the community and do some kind of outreach and actually talk to the people that we're forecasting for. So I thought we'd start out with a picture of our office. This is, I think it was in 2020, 6 years ago now. One thing to note is that's our big Doppler radar up here. So if you have a weather app and you're looking at the radar on your weather app, that's actually coming from our office if you're within about 100 miles of Pittsburgh. And we're going to be talking a lot about weather balloons to start out this talk. And so this is our upper air shelter here, which is where we launch and prep the weather balloons. So we'll be talking about that in a little while. You can take over this.
So just a little bit about the National Weather Service in Pittsburgh. We're a dedicated team of 19 members, 12 meteorologists, 3 electronics professionals and IT, 3 admin meteorologists, and 1 hydrologist. We are open 24/7, 365 days of the year, and we're one of 122 forecast offices around the country. We serve Eastern Ohio, Northern West Virginia, and Western Pennsylvania. And you can find more information on the weather and the forecast at weather.gov/Pittsburgh. So part of our mission is to protect the life, is for the protection of the life and property of our citizens, as well as the enhancement of the national economy. One of the many things that we do is we do the forecast, your warnings. So in the summer when you see those severe thunderstorm warnings or the tornado warnings, those are us. We do decision support services. So basically some forecasts for emergency management for big events such as like Picklesburg or First Light. And then what we're doing today is we're doing outreach. So today's big topic is weather balloons. So that is one of the ways we do weather monitoring. So we do it twice a day. In the winter, we launch around 6 a.m. and 6 p.m. And during the summer, during daylight time, we do 7 a.m. and 7 p.m. From this launch, we get a picture of vertical profile of the atmosphere. So we measure our temperature, dew point, wind speed, and wind direction to kind of give us an idea of what that vertical profile is. It definitely does help with our winter precipitation. Because it just shows us what the temperature is where we have moisture in the atmosphere versus dry air. On the left, you see the sounding. This is actually from this morning. We have an area of dry air here and an area of moisture. So right here, you can assume that there is actually clouds.
Yeah, so we call this a skew T, the map, the graph on the left. And you can imagine it as the ground being at the bottom and then up in the atmosphere, the higher up you go. So the red line is the temperature that's being captured by the radiosonde, the balloon instrument, and the green line is the humidity. So when those are very close together, the dew point and the temperature, you have a moist atmosphere. If you go all the way up to the top where they're further apart, you have a much drier atmosphere. So that's one of the things that you can see quickly on a skew T like this.
So here is a map of all the locations around the United States that do launches. There's 92 areas that do launches. And worldwide, we have at least 1,300. And we all do them at the same time every single day. So every single location that does these launches does it at what we call UTC time. So 12 UTC, which is what I said right now is 7 a.m., but we launch 1 hour early at 6 a.m. And 0 UTC, which is 7 p.m., and we launch at 6 p.m.
The whole idea of weather balloons and radiosondes really is to get kind of a snapshot worldwide twice a day of what's going on. So we have, airport weather stations, we have home weather stations, we have satellites, but this is another way of getting that data that's actually up in the atmosphere instead of on the ground, because we don't have a lot of other observations up in the atmosphere.
And it's a video.
Maybe?
Okay, so what right now we're going to be showing is the process of inflating the balloon.
Yeah, so if you thought this was an ordinary party balloon, you would be wrong. It is much bigger than that. This is obviously time lapse as well. So the next step after inflating it, which we do use helium, we use hydrogen.
Yeah.
Some offices use helium if they're in close contact with like a school or something, since hydrogen is a little bit dangerous. It is not. Maybe. There we go. After we inflate the balloon, if it loads, there we go. We have what we call twine, a big spool of string that we will tie it off with. So that's me tying it off. If you notice the balloon, the rubber band ball in the back, all the bags that the balloons come in have a rubber band, and so we've been doing this at this office since, I believe, like the 70s. Every bag has a rubber band. They've been pulling it off and creating this rubber band ball. So I don't even know how many rubber bands are in that rubber band ball, but it's quite a few. So that's tying off the balloon there. You'll notice that we did tie a parachute to it, and we'll talk a little bit about that in a second. This is what an actual launch will look like. And you can see the orange parachute there tied to the balloon, and then at the very bottom is the radiosonde. So actually, we brought a radiosonde here. This is the instrument we use that picks up the temperature, dew point, humidity, and it has GPS on board. So as it's moving, we can derive what the wind speed and direction is based on the location and how it moves. So this is just tied here to a string at the bottom of the balloon. It has an antenna on the bottom, which sends back data to our computer down on the ground at our office. And every second that updates throughout the entire flight, which takes 2 to 2.5 hours, depending on what the weather looks like that day, how fast things are moving. And here, I'll show you the balloon. Unfortunately, we don't have any hydrogen with us to inflate it, but you can imagine this is about how big it is, uninflated, and how big it gets. Now, this is super stretchy. As it goes up in the atmosphere, the pressure decreases, so the pressure on the inside actually pushes this and expands it, and by the time it pops, which is roughly 21, 22 miles up in the atmosphere. It'll be probably about half the size of this auditorium, very large. It goes up, obviously very cold up in the upper atmosphere, so the latex becomes very brittle. Eventually it slows down, and the frozen latex pops, shatters, and luckily for the people on the ground, we tie a parachute to it. So the parachute comes down. Let's see if I can get it to open. Maybe. The parachute comes down and slows the landing a little bit. So far, we haven't hit anyone that we know of, but people do find these in their yards every now and then. And we used to actually have a mailbag on the balloon itself, so if people found the radio sign, they could mail it back to us. We found that most people that found them either trashed them or kept them as souvenirs, so we stopped putting mailbags on them, and it's actually just cheaper for people to throw them away themselves, or if you find one in your yard, keep it as a souvenir. They're harmless. So I think the next slide that we had, let's see. Here is a video of what it looks like if we launch in very strong winds. So this doesn't happen too often, but when it does happen, it's always very interesting. I believe this was the Albuquerque office, and they're launching in, I don't know, 40, 45 mile an hour winds. Working at the Lake Charles, Louisiana office, I did get to launch a few times in tropical storms, so that was always interesting when the parachute catches the wind and it's basically pulling you sideways when you're trying to launch. So, all right. The next slide is something, is a new tool that is not something that we own, but something that the community has created over the last 5 or 6 years. It's called sonhub.org. So we have computers at our office that are actively tracking these radio sondes as they're launched and fall back to the Earth and collecting the data for scientific purposes. But the ham radio community has actually put together a website that is also tracking the radios on these radio sondes in real time, and there are actually people that will go out tracking them and try to find the balloon. So this is actually the radio sonde and balloon that we launched about an hour ago or so at our office in Moon. There's the track that it's taken so far. And the site is cool because it actually can predict where it's going to pop and approximately where it's going to land. Actually, it's pretty good. So it's using a forecast model to predict that. And let me click it. And it'll actually tell you here all the live stats that are coming from the balloon. So 2.4 relative humidity. The temperature right now is negative 64.9 degrees Celsius. Let's see. The height right now is just over 21 kilometers. It even tells you the speed, so it's going up at 4.7 meters per second.
And you can also pull up the SKU-T live as well.
That's right, yeah, so she showed you the SKU-T earlier. Based on the data that's already come in, this is what the SKU-T looks like right now. So at the office, someone right now is actually going through the data, QCing it, make sure that there's nothing wrong with it, and eventually, once all the QC is done, the balloon's popped, they'll send that off to our headquarters for documenting and for archiving and then for the models themselves. The other really cool thing that you can do on this website is get an archive of all the places that the balloons have landed. So all these dots on the screen are actually places in 2025 that our balloon from our office has landed. So that's Pennsylvania there in the middle. We don't really go too far west just because we have westerly winds, and so most of the balloons are going to the east. But there are a few, depending on the day, maybe in the summer when we don't have a lot of strong flow, they can kind of float off to the west. The furthest east one, I think, is up here in Massachusetts, and Liana was telling me that was actually one of her balloons last January. So occasionally we get that far. I think it looks like we have one out in the Atlantic from last February as well. But really kind of all clustered here in Pennsylvania into New Jersey and Maryland, maybe parts of West Virginia. So let's see. I can make this full screen. Take it away.
All right. So the data from these soundings go into our models. One of the big models that we use is called the National Blended Models, where we use a bunch of models are put in together and kind of compare to each other. So they're combined together to kind of give us an idea of what the outlook is. So for example, we can ask, what was the probability of seeing greater than 30 miles an hour wind gusts? This will tell us our probabilities of seeing that. So the greater the probability, usually the stronger the confidence, the lower probability, the lower confidence.
This has really changed drastically even in the 10 years that I've been in the Weather Service, where as before we had, the GFS American model and the European model, and we were looking at these deterministic models and kind of, they're fighting each other for the solution, and you kind of go with one, go with your gut instinct, and you put out a forecast. Whereas now we have all of these different models that are excelling at different types of patterns, and each model has many different members of the ensemble that kind of give us that extra look at probabilities just depending on the different initialization of the model itself. So we may have an ensemble that has 100 different members in the model that are all tweaked a little bit to give us an idea of what's actually going to happen.
So another way to visualize this is through this graph. So as you can see, these lines we have a lot of lines that are really close together. So in this case, we'd be strongly confident that, we're going to get 1.5 to 3.5 inches. But in this case, we'd be a lot less confident because there's a lot wider of a range. So typically, we have the mean there, but it could really go any way. It could go lower or higher. Typically, the mean can sometimes wash out our higher probabilities, because sometimes we can have a lot of high outcomes and a lot of low outcomes, and here's the mean right in the middle. So sometimes in those cases we have to kind of communicate how there's just two different outcomes, even though we're showing a mean value.
Emergency managers are really kind of our core partner. So we're working very closely with Pittsburgh Emergency Management and ahead of the marathon, ahead of first night, that sort of thing. So what probabilities really help us to do is not just give them a single forecast number, but give them an idea of what our confidence is, give them an idea of the worst case scenario. So if this were the forecast for first night, we would communicate that blue line, which would be probably the mean, the best forecast, but give them an idea that, hey, there is a chance that we could see up to 20 inches of snow. So if that crosses a threshold, which it would here, 20 inches is a lot, prepare for the worst case, which, 15 to 20 inches of snow, but the most likely is, 3 inches on this graph. So that gives them an idea of what to plan for, and they're not just looking at this actual forecast, and instead if something goes wrong with the forecast, they can react to that appropriately.
So this kind of leads us into some winter precipitation types. So like I said, we have the balloon gives us a vertical profile. So one of the biggest things that helps us with in the winter is which type of precipitation are we going to get. So we have the snow, the rain, so the whole atmosphere is below freezing, the whole atmosphere is above freezing, but we can have at times where we have a bit of a warm layer mixed into that vertical profile. So with sleet, we have a very shallow, small, warm layer where we have enough time for the snowflakes to melt into droplets, but then there's plenty enough time between the bottom of that warm layer and the surface for it to refreeze into just little balls of ice. So in the freezing rain, it is a big enough warm layer where we melt all the rain, but there's just this shallow cold layer on the bottom, so the water doesn't have enough time to freeze, so it will hit the surface and freeze instantaneous. So if you think about those experiments online where you stick a water bottle into a freezer, and then after a certain amount of time you take it out and then you hit it on the ground and it instantly freezes. That's what we call supercooled water droplets. And that's what really happens with freezing rain, is it freezes on instant contact because it is below freezing, but it's still liquid. So this is another way to visualize our different types of precipitation. So here's your freezing rain. Like I was mentioning, you have the snowflakes, they melt into water droplets, but you have a really shallow cold layer on the bottom, so not enough time for it to refreeze, and it'll freeze on contact with any object or even the ground, depending on what is actually below freezing. Then our sleet, also showing our shallow warm layer here, melting it, but then having enough time to refreeze it into balls, little, usually ice balls. And then we have our snow. Our snow is just temperature is completely below freezing the whole time, and it comes down at snow. But snow is not all just straightforward. So typically when we go into snow forecasts, we go in with the idea that we have, for every 10 inches of snow, we have 1 inch of rain. So that's what we call the 10-to-1 ratio. So that's what we're looking at. But when you have like temperatures near freezing, typically that means the snow is going to be wetter. So that ratio is going to be lower, such as like 7 to 9 to 1. So every 7 to 9 inches of snow, you have 1 inch of rain. But when you have the really colder, drier air, you can have the really drier snowflakes, and you can get as much as 20 inches of snow to 1 inch of rain. So this is just kind of some images illustrating that. So like what we were talking about with the wet snow is really heavy. It's that really heavy slush. Even 3 inches of heavy wet snow can be difficult to shovel. But it could also, looking at even the same amount of snow on one sort of surface, you can have a different amount of weight on that surface. So the lighter the snow, the fluffier, the less heavy it is.
Snow is definitely the hardest thing that we forecast in the Weather Service. And like she was showing, the difference in a degree sometimes is the difference between all rain in Pittsburgh or all snow in Pittsburgh, or a mix of freezing rain and sleet and snow. And so a few degrees, we have to be right by a few degrees up in the atmosphere to get the amount right, and then we have to get the snow ratio right, even if we're getting the liquid precip right, just because the ratios can differ so much. So we'll talk a little bit about some of the different patterns that Pittsburgh sees, or the country sees, and how they affect Pittsburgh. The first one is the Alberta Clipper. We've actually had several of these this year that have produced quite a bit of snow for December. I think it was the 8th snowiest December on
10th.
record. The 10th snowiest December on record for Pittsburgh. And our records here go back to the 1870s, I believe. So the Clipper system, it looks like this, where you get a low pressure that's quickly moving out of Alberta, Canada. It moves across the Great Lakes somewhere into our area and then exits pretty quickly to the east. These sometimes can be tricky because they're not always forecast very well. The Clipper moves through really quickly, and we can end up with a very dry system and not a lot of snow at all, or just enough moisture, but a very cold system that we get very fluffy, dry snow and snowflakes, and we end up with a quick 5 inches or something out of it. The next one is called the Colorado Low because it's moving out of Colorado. The low's there, the big L. And it moves across somewhere in the Midwest, and depending on where it goes, we could get all rain or all snow. These are the ones that produce a lot of mixed precipitation for us. So depending on how far north the low goes, if it goes too far north, we'll be in the warm sector and end up with all rain or a mix of mixed precipitation. If it goes a little bit further south, it's better for snow for us, because we'll be a little bit more in that cold air, and we end up with more snow. These are usually the bigger producers for us, just because they move right over our area, and some of the bigger snowstorms that we've had in history are these Colorado lows. The third type is the nor'easter, which you may have heard before, which really rides up the East Coast. We're kind of outside the normal track for these. These tend to be a little bit further east, but if the storm system is big enough, these can produce quite a bit of snow for us as well. If anyone remembers the storm of the century, 1993 in March, Pittsburgh got tons of snow. I was actually in Georgia at the time. I was 2 years old, and we had blizzard conditions in Atlanta. A storm track very similar to this developed over the Gulf Coast and tracked up the East Coast and produced tons of snow all the way up and down the East Coast. So not very common snow producers for us, but when we get a lot of snow from these, they're very historical. One of the final ways of getting snow for us is lake effect snow. Now for us, we cover all the way up to I-80, all the way south down to Morgantown. For us, most of the lake effect snow is going to be up in the I-80 corridor. If you read our area forecast discussions daily, we talk about I-80 and the I-80 corridor all the time because it'll be dry everywhere else. I-80 is getting snow. This was actually, what was this? This was last week, the 30th, I believe.
New Year's Eve, the day before New Year's Eve.
December 30th, we actually had a lake effect band that wasn't off of Lake Erie, but was actually catching the water off of Lake Michigan. So we had this lake effect band that was coming all the way down from Michigan, across Ohio, and just really sat over Washington County for 6, 7, 8 hours. I was working the night shift that night, and bands like these are very hard to forecast because they're happening at the micro scale, things that the models really aren't very good at forecasting. We know that a band like this could set up, but we don't know exactly where it's going to set up. And the real problem with that is if you're under the band and it sits there for a while, you can end up with 8 to 10 inches of snow, whereas if you're in Pittsburgh, you end up with 2 to 3. So we sat there that night and we kept thinking, okay, it's going to move, it's going to move. The models show it dissipating, and it did not dissipate, I believe, until like 11 or 12 that afternoon. And so if you were in Washington County, you woke up with 8 to 10 inches of snow on the ground when we had 2 to 3 in the forecast.
Yeah, but even, Washington, it was mainly like Washington City, right? So some even areas north and northern Washington County and southern Washington County, they got nothing. They're like, what are you talking about, snow? Meanwhile, we have this whole line right here of high snow accumulation. It was quite incredible.
This is the kind of storm that keeps you up at night because you really can't forecast, at least with today's modern technology, something on a scale like this. And so we had a staff meeting earlier today and we talked about this for several hours. And honestly, it's kind of puzzling at how this set up exactly where it did and why it lasted so long. So that's probably a good case study that we'll look over in the summer when we've moved on from snow. The other thing you might have heard recently in regards to snow is called a snow squall. So this was a cold front that came through New Year's Eve and early New Year's Day. It pushed through Pittsburgh just after like midnight to 1 a.m. A snow squall is just a very intense, in the summer it would be a thunderstorm, a line of thunderstorms, but in the winter it's a snow squall. It's a very intense, rapid drop in visibility. Sometimes you get very quick freezing temperatures afterwards, so any snow that falls quickly covers the roads and you get whiteout conditions. And these are very dangerous, especially on the interstates where you've got people driving quickly. They run into a big wall of snow and suddenly you've got multi-car pileups. We have problems every year on I-80 with snow squalls coming through and having tons of cars just end up in the ditch and all over each other. And we've got some screenshots there, some big snow squalls that have happened in history. But if you see a snow squall while you're driving on the road, the best thing to do is try to pull off if you can, get off as soon as possible. They don't really last very long. If you see the radar animation there, it moves through very quickly and then the most intense part is gone. So, 5, 10, 15 minutes at most, usually.
Yeah, and sometimes they can get some lightning with that too. Like there was a lot of reports of lightning with that particular snow squall band that went through on New Year's Eve, New Year's Day.
We did, yeah. We had a few lightning, not a lot of lightning strikes, but a few lightning strikes.
Yeah.
It's always fun to see the thunder snow. So people like to get an idea of the climatology of snow in Pittsburgh. How many times do we see certain amounts? Generally, on average, we see about an inch of snow 13 times a year. So those tend to be our little nickel and dime snowfalls. Maybe just some leftover lake effect from Erie, or we have a storm come through, we get some rain, some mixed precip, and we get a little bit of snow on top of it. About every 2 years, we get a good 6 inches or more, which is actually winter storm warning criteria for us. That's when the impacts are pretty severe, travel's not great. If you're in Pittsburgh, you're struggling with the snow plows and the salting, and so travel's probably going to be good for at least a day or so, depending on where you are and how quickly the roads are plowed, and how cold it is once the snow falls. 8 or more inches is every 4 years or so. I think we're overdue for that. Our last big snowfall was probably 2020, December 2020. And then 12 inches or more, I haven't seen that, I don't believe, since I've been here. I think we got close in 2020, but every 14 years. And then 16 inches or more, it's once every 72 years. So I honestly don't know if we'll see that again in Pittsburgh. We'll have to see. The other question I always get asked by people who find out I'm a meteorologist is, why is it always so cloudy in Pittsburgh? Everyone wants to know why it's always so cloudy. Each year, on average, there's 203 days in Pittsburgh that are cloudy, which is 56% of the year, so half the year is cloudy. And comparing us to 3 other cities, we'll see how we compare. 226 days in Seattle, 222 in Portland, 208 in Buffalo, and there we are at 203. So we come pretty close to all those cities. We're not the cloudiest in the country, but we're awful close. 203 days is nothing to sneeze at. If you include all partly cloudy days, that goes up to 306. So that's 84% of the year that you're not sunny most of the day. So if you like sunshine, go to Florida. Why are we cloudy? Well, the main reason is our geography. So Pittsburgh, of course, is down here. We sit between Lake Erie and the Allegheny Mountains to our southeast. And so once we have a cold front that goes through in the winter after a big storm, we get flow out of the northwesterly flow. It flows over Erie, picks up moisture, and then slowly rises as our terrain gets higher and higher up towards the mountains. So what you end up getting, you squeeze all that moisture out, you get a bunch of cloud cover in here between Erie and the Alleghenies, and then it just really gets socked in, because that moisture can't go over the mountains, it gets stuck there. And so we get days and days of this northwest flow, days and days of just overcast, dreary skies in Pittsburgh. So this is the same kind of mechanism that gives us lake effect snow and then the flurries for days after we have a big storm coming through.
So where can you find some of our products? So some of the information can be found on our winter weather webpage, which the website's up here, weather.gov/Pittsburgh/winter. You can see all sorts of products, probabilistic snow forecast showing the expected snowfall versus, the high end amount and the low end amount, ice accumulation, onset end time, and snow ice observations, medium long range forecasts, and the winter severity index as well. So all those you can find on our website as well.
If you want to know the snow forecast, that's really the best place for you to go, because it does have the maps. There's also a table down below on the page that has individual cities, so you can see all this individual information, the actual forecast versus the high-end worst-case scenario, the low-end amount for each individual city as well.
And so the last thing we want to talk about is just kind of the winter criteria when it comes to our products. So you've heard the winter weather advisory, the winter storm warning. So the first start is this winter storm watch. We usually put that out about 2 to 3 days ahead of time, depending on our confidence. That's usually when we're looking at least a 50% chance of exceeding a winter storm warning criteria, which is at least 6 inches of snow or more. As we approach closer to the day of a storm, we'll look at, okay, what are we expecting? What's the probability if we're going to get 3 inches or more or 6 inches or more? And that's how we'll end up putting out either a winter storm warning or a winter weather advisory. What also falls under the winter weather advisory is freezing rain. So if we're expecting freezing rain, but under about a quarter of an inch, we'll put out a winter weather advisory. But if we're expecting at least a quarter inch or more, we'll end up putting out what's called the ice storm warning. And for all these warnings and advisories, we're looking at least an 80% chance or 80% confidence in these outcomes. Our blizzard warning we're looking at more of the winds and visibility. So we're looking at sustained winds of 35 miles an hour or greater for at least 3 hours or more and causing at least a quarter-mile visibility. So we can have a blizzard warning but not have snow falling. So basically we can have a blizzard warning because of blowing snow, reducing visibility for multiple hours.
Luckily, blizzards are extremely rare for Pittsburgh. I don't know that we've ever had one for the city itself. And most of the time when we issue blizzard warnings, they're up in the mountains for us. We have, we average one every 10 years or so.
Even though we put out, one last year?
Yeah, we did. We did have one last year. Before that, actually, the most recent blizzard warning was from Hurricane Sandy in 2012, because we actually had some cold air move in behind the storm that got drawn into Sandy, and in the mountains that ended up being blizzard conditions with lots of snow. So hurricane can produce snow. So with that, we'll take any questions that you have, and we have plenty of time, so any questions?
How do you interface with like local stations like KTPA and all that? Do they have your data?
It's kind of a mix. So the stations are set up in a very different atmosphere where, they're coming in at 2 a.m., they have an hour or so to quickly make a forecast, and then they're immediately on air with their forecast. So a lot of times they'll come to us asking questions. We put briefings. So we have a Slack chat room where we're constantly chatting with all of our partners, including our broadcast meteorologists. So they're coming to us asking questions. We're going to them, telling them stuff. Here's what we think. What do you guys think? So it's kind of a collaboration between us and our broadcast partners, just depending on what they need, what we can give them, how we can support them. A lot of times, if there's something we want to get ahead of in terms of a message that we think should be out there, we'll put that in the Slack chat room and say, hey, we think this is going to happen. We want to kind of hit this really hard. Can you guys kind of run with this message? And they'll take it and run with it as they need to.
Hi. So I remember you said that we have about 203 days with no light. So in comparison, a place like, say, Miami or Los Angeles, what would they have?
Los Angeles is probably going to be much lower in terms of cloud cover, just because they really don't have a lot of rain on the coast there. The fog there will be interesting because they do have a lot of fog, typically in the morning times, a lot of marine fog that rolls in from the ocean. I'm not sure exactly what the number would be, but I would think that they have a lot more sunny days than we do here. Florida, same sort of thing. Most of their cloud cover is going to come from either big systems like hurricanes or just general thunderstorms in the summer. So you're still going to have a lot of periods of sun, even during the summer when you have thunderstorms. And you're not going to have the solid cloudy days like we do here. You don't get socked in for days. So much more sunny weather in Florida and California.
I mean, like just a rough guesstimate or like...
I don't have a number.
I would say probably over 200 days in Florida where you have at least sun part of the day. California may be something like that too, just with fog instead of a lot of cloud cover.
I have a question for you.
Yeah.
What major weather event in our region do you wish people would listen to you more about? Like, is there is there an extreme weather event or something where you give a warning or there's some kind of advice you give and you wish people would listen to you more?
Ooh,
Tough one.
I don't know if I can pick a single one. Do you have a good answer for that?
I don't know. I haven't been doing this long enough, but the one thing I can think of is more when we have those uncertain winter weather events. It's just really trying to tell them, hey, we're looking at this, we can see this, it's going to happen, this could happen and this could happen, but we're really not sure because all the models are like changing from day to day. Like that snow band that's set up in Washington City, some of the models showed like a slight chance of it, but it kept moving northward. When we were looking at it during our meeting today, it kept moving northward like every single model run until the day of. So things like that can happen. So it's like more understanding that, and especially with one of those things where we have mixed precip, that's really difficult to do because even during the day of the storm, it could shift. It could shift on us, and then instead of getting 6 inches of snow, we're looking at rain. So it's kind of like trying to help them understand that we're trying our best to forecast this for you, but there's just still so much uncertainty with these storms. None in particular that I can actually think of, but that in general.
So, sort of related, but the most challenging part of our job isn't actually the forecast itself, but in getting the message of the forecast out to the public. And today we're competing not with just other meteorologists in the enterprise, but also with everyone on social media who has a Facebook page related to weather, who may or may not know what they're talking about. All the different apps that are on your phone that give you a number but may not give you the context for that number. So someone's weather app a week out may say that we're going to get 12 inches of snow, and of course that was one model run. That forecast quickly changed. But that's the number that's stuck in people's heads. So when we don't get the 12 inches of snow a week later, even though we've been saying, it's only going to be 3 inches, well, everyone was wrong because that one model run days ago, or that big GFS 7-day forecast that had 12 inches of snow on it, that was on Facebook somewhere, someone posted. That is what the number that sticks in people's heads, even though that wasn't the actual forecast. So that's always challenging for us.
Could you explain to me what is a microburst and your ability to predict that? We got hit with one in Lawrenceville in 2018. We just moved here. It wasn't fun.
Yeah, so microburst, it's a type of thunderstorm that really happens on a day where you don't have a lot of wind, a lot of flow at all. So the thunderstorms, they bubble up. In order to have a microburst, you have to have a lot of dry air aloft. So you've got the updraft and the thunderstorm that's going up. Eventually that cool air is going to chill the rain that's being brought up into the updraft. You're going to get a lot of ice up above in the top of the thunderstorm. And eventually that ice becomes so heavy that the thunderstorm can no longer contain it. It drops out, and you get this sometimes hail, but a lot of times just very cold wind that comes down to the ground and splats out in all directions. So you end up with 70, 80 mile an hour winds over a very small area. And I know I was actually on shift that day. I believe it hit Lawrenceville, which is where I live. It also hit parts of Millville too. In fact, there's a video from Grist House in Millville, the brewery, of people scrambling for shelter as this wall of wind really comes through. And they actually named a beer after them, I think it's called Microburst. But they're becoming more predictable, but the problem with microburst is we don't know exactly where that thunderstorm is going to occur a long time before it occurs. We know that it may be a good day for microbursts, but there's no way of saying, well, Pittsburgh's going to get microburst today. We know kind of the general area. The other problem with microbursts is that they don't develop really from the ground up. We usually see them on radar much higher aloft, and then by the time you see them, you maybe have 5 to 10 minutes max before they're coming back down and bringing that wind down to the ground. So at kind of where the science is right now is we're not we used to wait to see them on radar to warn them, and by the time you get the warning out, it's basically happening right then, or it's already happened. What we've done in the past few years, we've gotten a lot better at it, is trying to look at some predictors before we actually see it on radar so that we can put a warning out 5 to 10 minutes in advance of this actually developing. So people on the ground have 5, 10, 15 minutes of lead time. It's still not a lot, but it's enough to get people inside to know that there's going to be significant wind come down. So as things get better, as models get better and better, hopefully we can increase that lead time even more.
From our online audience, we have a question. In what ways do you see winter weather patterns changing?
So as our climate warms, one of the things that we have been seeing, which is actually counterintuitive to warming, is that Lake Erie stays ice-free for longer and longer periods of time. Now, we talked about Lake Erie several times in the presentation. Lake Erie is a significant moisture source for us in the winter, so we see lots of our little snowfalls come from Lake Erie. Usually we see Lake Erie start to ice up sometime in January or February, depending on how cold the year is, how cold the water is. Once it ices over, that shuts off our moisture source, and then that's it for our lake effect for the year. As we see Erie stay warmer and ice-free longer and longer, we have more and more of a lake effect season. So, in the future, as we continue to get warmer, we might actually have more snowy days overall, even though a lot of our bigger snow systems kind of stay out of the area.
We've had a few questions online about some of the staffing and operations of the Pittsburgh NOA and NWS office. Can you kind of talk about the volume of people and staffing that you guys have working out of your office, and the number of kind of like the jobs you have and the types of people that work out of that office, and some of the different things they're responsible for?
Yeah. Pull up one of the first slides. We have, like 15 meteorologists that work. We have lead meteorologists, which are kind of our senior meteorologists. We have a general meteorologist, which we both are. We have a management team, so we have a meteorologist in charge. We have a warning coordination meteorologist who is kind of our liaison to the public and to our partners. So he's going to meetings with emergency managers across the area. He's the one meeting directly with some of our broadcast met partners. We have a science operation officer who is kind of in charge of putting together our training plans, doing any kind of research and heading it up, research in the office, kind of moving us forward in terms of the research to operations. We have a hydrologist, because we didn't mention flooding here today, but
That's true.
hydrology and flooding is huge in Pittsburgh. It's probably one of the reasons why we have an office in Pittsburgh, because river flooding and flash flooding are huge here. We have an administrative assistant who is just in charge of all sorts of paperwork and everything that goes on related to that. Who am I missing? We have electronics specialists who do things like keep our radar operating, go around to the different airports to keep our weather stations up and running, doing all sorts of IT and tech support. And we have we currently don't have an OPAL, but an observation programming leader who goes around, and we have a program called Co-op that is a volunteer-based program where people have thermometers and rain gauges, and they keep a record daily. Some of these stations have actually been going since the 1800s. So he goes around and makes sure everything is still sighted properly, everything's calibrated, keeps up with that sort of thing. Did I cover? We are a 365, 24/7 operation, so we work rotating shifts, typically 6, 7 in a row of like a night shift. Then we'll roll around to a morning shift or an evening shift. So I just got off a string of 7 night shifts yesterday, and now I'm on day shifts. So it keeps things interesting, though. The shift work, and the weather is always different every day, so there's always something different to look at.
And then one last question for you. Is there any extreme weather event that is potential or possible, or we've seen in the past or could see in the future, that actually scares you for Pittsburgh?
probably going to say some sort of major flash flooding or river
Yeah.
flooding.
Yeah,
That's
so-
really the big kill. We get tornadoes here in southwest PA, but most of our tornadoes are kind of small. They'll hit a house, cause some damage to a house, or cause some tree damage, maybe cause some car damage. But
Yeah.
the flooding is really the big killer in our area. So
Yeah, I would agree with that, because we did have one event this past year that was like that. I mean, I'm very new, so I never saw it before, but that's not saying much since I've been here for a year and a half. But like you said, that's going to be our biggest concern, because we have the 3 major rivers right at Pittsburgh as well. Granted, those are not much of a flash flood concern, but they can be a flooding concern. Fortunately, flooding concerns are a little bit more predictable than flash flooding, but the flash flooding is just really big around this area, especially because we have lots of hills and valleys. So a lot of that water that can fall on the top of the hill can just funnel down into the valleys, and that's where we get some of our floods from the streams. Basically, it's usually the smaller tributaries that actually flood rather than our large rivers.
the terrain is really everything when it comes to flash flooding. And unfortunately, as Pittsburgh and surrounding cities have developed, they put infrastructure in places that are known flood zones. So you end up with schools in flood zones or houses in places that flood every 10 years or so in the floodplain. I worked an event, I think it was last June, in Wheeling, West Virginia, where we got 3 to 4 inches in a very concentrated area north of town. All that rain ran down through the hills into the Little Wheeling Creek, and there was just basically a wall of water where the river and creek rose very quickly, swept homes away, swept people away in their homes, and I believe we had 8 fatalities in that as well. That's
Yeah.
the only flash flood
That's
emergency, which is the highest level of flash flood warning we can issue. That's the only one I've ever issued, and it was that night. So that'll keep you up at night.
Yeah.
All right, well, I'd like to thank you both for being here this evening. We loved your talk, and we really are excited to pay attention to the weather and to see what great things you have for us in the future. So I'd like to thank you on behalf of our audience, and thank you again for being here, and thank everybody in our audience online and in person. You have a great evening.
Thank you.
Thanks for having me.